Today we are going to continue talking about similar figures. Yesterday we defined similarity and said that to be similar, there are two requirements of the figures. What are those?
Corresponding angles.
Corresponding angles are congruent, and corresponding sides are similar in what way?
Ratio.
There's some ratio, scale factor, or proportion that relates those sides together. Okay? Angles are congruent, sides are in proportion with this ratio that we call the scale factor. Today we're going to talk specifically about triangles. So yesterday we talked about figures in general. Today we're going to talk specifically about triangles. If we're talking about triangles, then we have a postulate that is called angle-angle similarity postulate. It says if two angles of one triangle are similar, really it should say congruent, would be a better word there, to two angles of another triangle, then the two triangles are similar. So what this postulate says is that if I have two triangles, and I know that in those triangles there are two sets of matching angles, that's enough to say those triangles are congruent, or rather are similar. So yesterday we said that to be similar, all of the angles have to be congruent. Well, really, if we know two angles are congruent, we know the third one has to be the same as well because there's 180 in a triangle. So if we've used up the same amount, we have the same amount left over. So if we know two angles, then we really do know that all the angles match. But the other requirement for similarity, that sides are in proportion, we don't know anything about. But this postulate says doesn't really matter. As long as we know the angles match up, that's good enough. In triangles. Only in triangles. It is not true in bigger figures because yesterday we looked at one where we had a rectangle and a square, and those are not similar to each other, even though all the angles match. So in triangles, if the angles match, then they're similar. But above that, this doesn't hold. Question?
How does that postulate work though? Because it could be like a scaling.
Postulate.
It could be a
So we
scaling
can't prove it.
triangle.
It could be a scaling, but the sides should still match up in that scaling. So there should still be a relationship that like this side and this side would match because they're between angles 1 and 3, and that this side and this side would match, and that this side and this side would end up matching up in the ratio. It's postulate, so I can't prove it. But it does tell us that those sides should still match up. That's why we didn't have an angle-angle-angle congruence when we talked about congruent triangles. Knowing the three angles are congruent doesn't mean the sides have to be the same, but it does, according to today's postulate, mean that there is a relationship between the sides.
Is a AA similarity postulate, is that actually the name, or is that just kind of like the 5-4 postulate, or is that actually what it's called?
That's actually what it's called. The book probably says like a number to go along with that, like theorem 7-1 or something like that, or postulate 7-1. But this is actually the name, is angle-angle similarity. All right, we're going to do some examples then. For our first set of problems, we're going to start with two triangles. And we are going to be told that triangle ABC is similar to triangle DEF. Okay, that is given here. Triangle ABC is similar to triangle DEF. So then a question. Is triangle BAC similar to triangle EFD?
No,
How can we tell?
because they are the corresponding angle.
Okay, so the names of the similar triangles are important because they tell us a relationship between the two triangles. Having A first in the first one and D first in the second one tells us that angles A and D are matching angles. Having B and then E tells us that those are matching angles. And then C and F should be matching angles. So when we reorganize our letters, we need to make sure that the matching letters are maintained. So in that new name, BE, that's still good. AF, that's not good, because A and F aren't the matching ones. So those two are not similar, because the right stuff isn't matching up. Okay, so that is a false statement. Next question about this same picture. If angle B equals 70, then how big is angle E?
70.
70. Okay, and similar triangles, the matching angles should be congruent. Okay, there's not a ratio for the angles, there's a congruence for the angle in similar figures. So those two are matching angles, so they should be the same. Next question. Is it true that AC to DF is equal to AB to DE? So what we need to do is look at, are we matching pieces here? So AC is talking about the side that is between angle 1 and angle 3. Just angles that are marked as one line and angle that's marked as 3 lines. Then DF, is that talking about the corresponding side? So DF is between the angle that's marked 1 and angle that's marked 3. So those are corresponding sides, that's good. That's how we set up a ratio, is we should be talking about corresponding sides. So then in the second one, AB is between the one that's marked as 1 and 2, and DE, is that the corresponding side to AB? Yeah, it's between the one that's marked 1 and 2. So we're matching correspondings with correspondings. If these two are similar, that should be true. Okay. I probably should be marking with little tallies because that means they're the same, so I don't know, we'll do like little squiggles, something. They're not the same, but there's a relationship there. They're corresponding. Okay. Last question with this picture. If DF to AC is equal to 8 over 5, then what is EF to BC? Okay, so we want to make sure that we're talking about corresponding sides here. So DF and AC, are those corresponding sides?
Yeah.
Yeah, they're the ones I already marked with one little squiggle. EF and BC, are those corresponding sides?
Yeah.
Yes. Are the fractions set up in the same direction? Meaning, is it the same triangle to the same triangle? Like the tops match and the bottoms match?
Yeah.
Yes. So both of the tops are talking about the bigger one, both of the bottoms are talking about the smaller one. So then what should that ratio be? 8 over 5. Okay, that scale factor should be true for the whole triangle. So we should have 8 over 5 for both of them. Okay? Questions on any of these? Yes.
When we're in the scale factor, can you choose which triangle goes in the bottom and which one goes in the top?
Yes. Unless the directions specify and say what is the scale factor of ABC to DEF, then we would have a specific way to do it. If it just says find the scale factor, it could go either way. The next question, if I have a right triangle with an angle that measures 37 degrees and another right triangle with an angle that measures 53 degrees, do those two triangles have to be similar? And how can we tell?
Yeah.
So according to today, what does it take to be similar?
2 angles.
2 angles being the same. Well, if they're both right triangles, they both have a 90-degree angle, so that's 1 for them.
But then the
Would
other,
they have another one that has to be the same?
yeah, because the other angle would have to be like on the 37 triangle would have to be 53 to equal that 180.
Okay, so in a triangle, we know we have to add up to 180, so we can figure out what the missing angles are, and it turns out that they end up being the other part of that. So these two triangles are similar because the angles are matching up. Okay, angle-angle similarity says if we can get the angles to match up, then the two triangles are similar. Questions on that? Our next example uses a picture that is similar, no pun intended, to many of your homework problems. And that is when we're going to have one triangle stacked inside of another one. Okay, so there are really two triangles in this picture. There is a small triangle at the top, and then there's the big triangle, that's the whole thing.
What is the 15 mark?
Oh,
The 15 is marking the KL segment. We are told that two of these lines are parallel, which means we get some special angle pairs in here. What angle would have to be the same as angle JIK? H. Why?
because if parallel, corresponding angle.
If we have parallel lines, corresponding angles should be congruent, and those are corresponding. They're in the same corner relative to those parallel lines. So then what angle would have to be the same as K?
Oh.
L. And J is the same as itself, so we've got some similarity here then. Okay, all the angles of the little triangle are matching the angles of the big triangle, so these two triangles are similar to each other. So then let's name them. Remember when we name them? Order matters. I can name the first one whatever I want, but once I've done that, the second one, the order of the letters matters. So if I name it JIK, what would I name the second one?
JHL.
JHL. So the matching angles are in the same position of the name. J matches J, I matches H, and K matches L. Since these triangles are similar, we should be able to set up ratios of their sides to solve for the missing letters of X and Y. 9 over 24 equals what over X? Okay, first let's figure out where these numbers came from. Where does the 9 come from?
JK.
JK. Okay, so I'm going to call that little right. Okay, it's the little triangle, and it's the right-hand side of the little triangle. Where did that 24 come from?
9 plus 15.
9 plus 15 is 24. So what does that represent then?
That side.
The big right. Okay? It's the big triangle's right-hand side. We always want to be making a comparison of little triangle to big triangle. You will never use that like 15 all by itself because it is not a piece of a triangle. It's a part of a side of a triangle. Okay? We need to be comparing triangle side to triangle side, and 15 is not a side of a triangle. It's a part of a side of a triangle. Okay, so 9 is the little triangle's right, 24 is the big triangle's right. What does the X represent?
The big triangle's bottom.
The big triangle's bottom. So what would that match with?
The little triangle.
The little triangle's bottom, which is 12. Okay? Questions on how to set up the ratios. Always want to be making the comparison of matching sides, so right to right, left to left, bottom to bottom, and little triangle to big triangle. Not a part of a side of a triangle like the 15, but a whole side of a triangle. So we use 24. To solve this, we learned yesterday that we're going to cross multiply, but you don't have to reduce before you do that. I like to do that because that gives me smaller numbers and I'm not good at arithmetic. So I'm going to take 9 and 24 and reduce it, and they reduce by what? 3.
3/8.
To give me 3/8. That gives me numbers that are easier to multiply. So when I cross multiply this, I get 3x equals 96. And x then equals 32. Yes?
Could you simplify 12 and 8?
You cannot simplify 12 and 8.
Nope.
If I want to solve for y, if 3/8 was the scale factor for one part of this, 3/8 should be the scale factor for any relationship in here. 3 was representing the small triangle. So if I'm trying to solve for y, then I'm looking at the left-hand sides. What is the small left? 6. What is the big left?
Y.
Y plus 6.
Yes.
We're never going to use the y and the 15 by themselves because they're not a side of a triangle. They're a part of a side of a triangle. So the little triangle has a side of 6. The big triangle has that whole thing, 6 plus y. Now when I solve this by cross multiplying, I'm going to multiply and get 48 for 6 times 8. And when I multiply the 3 times the y plus 6, what do I need to do?
Distribute it.
Distribute. I need to multiply by the whole thing. So I distribute that 3y plus 18. Subtract 18 from both sides. 30 is 3y. So y is 10. You will have several problems like this on your assignment. So do you have any questions on how to set up these ratios or solve them?
Is there any way to do them fast?
No. No, sorry. Practice makes them go faster. Like I can do them faster than you can because I've been practicing them for a long time. But no, there's no there's no shortcut that I'm not teaching you. I have one more example I want us to look at. Celia is going to measure the height of a tree for a biology class. And what she does is she stands in line of the shadow. So here's the sun. Making a... Oops. Whoop. There goes the sun. Okay. Whoop. Let's try again. All right.
I'm not the only one who thought about that. The Beatles, your Jones system.
Okay, so
Thought about it too. I love that song.
the tree makes a shadow on the ground because the sun is shining on it. And what Celia does is she lines herself up. Impressive, right? She lines herself up with that so that the end of her shadow is the same as the end of the tree shadow. Okay? So she steps herself in line so that the shadow to her head is the same as the shadow to the end of the tree. This, I know, right? It's amazing. It's amazing. That makes 2 triangles. We're going to put some labels in here. S for shadow, C for Celia, T for tree, H for head, and I have no idea why the book calls this R, but there we go. We've got labels for everything now.
R. Wow.
I'm thinking like tree. Like that's why they labeled it R or something. I don't know.
L for leader.
Where's the second triangle? So
Celia makes a triangle,
oh.
and the tree makes a triangle.
That makes sense.
If Celia measures her shadow, and it is 0.8 meters long, where would I put that in my picture?
From her
SC is 0.8. Her shadow is 0.8. Shadows are on the ground, so that goes on the ground piece there. If the tree shadow is 5 meters long, where does that go?
CT. No.
Oh, ST.
ST, because both shadows end at the same place.
I did that.
If her height is 1.6 meters tall, we want to know then how tall is the tree. So I need to set up a ratio that can help me find that S. What would be my scale factor to set up that compares similar parts of the triangle?
0.8 over 5.
0.8 over 5. So that's shadow to shadow. Okay? That's small shadow to big shadow.
Can you do decimals in a fraction?
Technically.
Not in a simplified fraction. So if we wanted to actually simplify and reduce this out, then we shouldn't have them in there. But originally setting it up, it's okay to have them in there.
How would we reduce it?
Multiply top and bottom by 10, and then reduce them. What is the second ratio going to be?
1.6
S.
Okay, so the scale factor is where we know both numbers. We know the shadows. So small shadow to big shadow. Our other ratio is going to be height to height. Small height to big height, hers to the trees. To solve this, we're going to cross multiply. 0.8x equals 8. And divide by 0.8. And 8 divided by 0.8 is 10.
10
So the tree is 10 meters tall.
Window, 10.
I think that picture deserves to get you the art teacher position.
I know. She's jealous, really. Mrs. Dover is very jealous. We've talked about this. She's working through it. It's okay. Any questions?
Neck
Are
longer
we
than the
gonna have to do
body.
these?
You'll have a problem similar to this, yes.
Are these gonna be on exams?
Yes.
Her neck's longer than her body.
Your homework's from 7.4 tonight.